So buffer effectiveness. The relative amounts of acid and base is one factor that influences how effective a buffer is. So the buffer will be most effective, able to absorb or minimize as much change when the concentration of acid and base are equal. So if we look at two 1 liter solutions of a generic buffer that has a pKa of 5, we can calculate the percent change in pH when 0.1 moles of sodium, 0.01 moles of sodium hydroxide is added. All right, I guess we're supposed to do that. So we have to do our stoichiometry thing, right? So we've got the sodium hydroxide is going to react with the acid, and it's going to make A minus and H2O. So if I'm adding 0.01 moles, I'm missing something here. Hang on. Okay, this is what I was missing. This is why that problem didn't make any sense. Okay. So here's solution 1, where we have equal moles of the acid and the conjugate base. Initial pH is 5, and we're adding 0.01 moles of sodium hydroxide. So that is going to react with some of the HA so that all of the hydroxide goes away. We've lost 0.01 moles of the acid and gained 0.11 moles of the conjugate base. So from this, we can calculate the pH using the Henderson-Hasselbalch equation. So pH equals pKa plus log of the base over the acid. So pKa is 5.0. And these are 1 molar amounts, so the base is now 0.110 molar. And the acid is 0.090 molar. Five plus log of 0.11 divided by 0.09. 5.087. How would we calculate the percent change? We'll look at the difference between the new pH and the old pH and divide by, we could divide by the average. That's a pain. I think we'll just divide by the original pH. So pish posh.
Does the pH always equal to pKa?
If the moles of acid and base are equal, yes. Because then this term is 1 and the log of 1 is 0. So I've got a 1.7% change. This is pretty small. Okay, so let's look at the other one. Here we've got 0.18 moles of HA and 0.02 moles of A minus. So much less of the conjugate base. Again, adding the same moles of hydroxide. And so we're going to use the same equation. pH equals 5.0 because that's the pKa. We're not using the initial pH, we're using the pKa. Plus the log of the base, which is 0.03 divided by the acid. Which gives me 4.247. It started out at 4.05. So minus 4.05 divided by 4.05. And that change is 4.9%. Which is definitely higher, right, than 1.7%. So the buffer that has equal amounts of acid and conjugate base to start with will be able to absorb more base or acid that's added, and the pH will change less. Any questions?
Repeat that again.
Yeah. Let's see. So this base had equal amounts of the acid and the conjugate base. This one had a lot of the acid and a little bit of the conjugate base. So you might think that this one would be better at absorbing sodium hydroxide because it has more acid, but it actually isn't. You'll get less pH change when you have a buffer where the concentrations are equal, and you'll get more pH change if one or the other is significantly higher. Did that help? So to be reasonably effective, the relative concentrations of acid and conjugate base should not differ by more than a factor of 10. This is just kind of a rule of thumb. Or in other words, the ratio of base to acid should be between 0.1 and 10. At 10, the base would be 10 times more concentrated than the acid. At 0.1, the acid is 10 times more concentrated than the base. So that's just kind of a rule of thumb. So relative concentrations are important. Absolute concentrations are also important. So the buffer's most effective when the concentrations of acid and conjugate base are high. We're going to look at that same generic buffer, but now solution 1 is going to have concentrations 10 times higher than solution 2. And we're going to look at the pH change again. So calculating the new pH. pH is pKa plus the log of the base over the acid. So here I've got 0.51, and the acid is 0.49. Five plus log of 0.51 divided by 0.49. So the new pH is 5.017. Doing the same thing over here. So the base is 0.06 and the acid is 0.04. .176. So even without doing a percent calculation, we can tell that this changed by a higher percentage, right, than this one. Anybody want to see the percentage? You guys are really chill tonight. Well, I don't feel like doing it, so I'm not going to do it. We can calculate the outermost points of the effective pH range. And we're going to use that 10-fold measure. So the lowest pH is where the base is equal to 0.1 of the acid. So the pH will equal, not 5, a pKa, plus the log of the base over the acid. Well, the base is equal to 0.1 acid, right? So 0.1 times the acid concentration divided by the acid concentration. So those guys cancel out. And just to make sure it's still true, the log of 0.1 is -1. So here we have pKa -1. Looking at the highest pH, where the base is 10 times the acid, pKa plus 10 times the acid. The log of divided by the acid. And so this is going to get us pKa plus 1. So the most effective pH range for a buffer is plus or minus 1 pH unit on either side of its pKa. Any questions? All these calculations that we've done so far are not to teach you how to do the calculation, but to kind of show you that what I'm telling you actually has some basis in fact, and it's not just something I made up. So the effective range is 1 pH unit on either side of pKa. So there are situations in doing experiments or whatever where you need to pick a buffer, or you need to make a buffer. And generally you need the buffer to be a certain pH. And so you can't just say, oh, well, I'm going to use this buffer and hope it works. You're going to choose it based on the pH that you want it to be. So you want the pKa of the conjugate acid that you're dealing with, the weak acid, to be within one pH unit of the pH that you want. So we can alter the pH of the buffer solution by changing the ratio of base to acid. It's going to be most effective at its pKa, and it'll become less effective as you go out, either higher or lower. So which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? So let's answer that question first. First, even before that, what is the sodium salt of an acid? What do acids do in water? They ionize, right? So if we look at this first acid, chlorous acid, we put that into water, well, this one. We're going to get hydrogen ions and chlorite ions. If we want to add more of the conjugate base to the buffer, we can't just add chlorite ions because they have to have a counter ion with them to be a neutral compound. So sodium is used a lot because, well, it's really easy to get and it's not toxic and you eat it all the time in reasonable quantities. So the sodium salt of this acid, we're replacing the hydrogen with sodium. So the sodium salt would be NaClO2. We really don't care what the sodium is. It has to be something, right? Okay, so if we want a buffer with a pH of 7.35, which of these guys should we choose? This one at the bottom, right? This pH by far is closer to 7.35 than the rest of these guys. So that's the acid we want to use, and we're going to use its sodium salt. So sodium hypochlorite. So if you have 500 milliliters of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? Well, we know what we want the pH to be, right? 7.35. So pH equals pKa plus the log of the base over the acid. So here the base is hypochlorite ion, and the acid is hypochlorous acid. Do we know what the concentration of the acid is? Yeah, we do, right? It's 0.1, they told us that, so we could put that number in here. Now, there's different ways that you can solve this. If logs make your head hurt, I would encourage you to use the solver on your calculator. Just plug it in just the way it looks, and it'll find it for you, okay? So I'm going to do it the other way, because logs usually don't make my head hurt. I'm going to take 7.35, I'm going to subtract 7.54. I'm going to take the anti-log of that, and multiply by 0.1. I'm getting 0.06456. If you're not using a solver, one of the ways you can check an answer like this is plug it back into the equation. 7.54 plus the log of 0.06456 divided by 0.1. 7.34996. Very close to 7.35. So now I know the molarity that I want in this solution. They've given me a volume of 500 milliliters. And they want to know the mass. So don't pull out the dilution equation or anything like that. Just use dimensional analysis. We're just going to convert units. What they gave us is the volume. So the volume is 500 milliliters. We can convert that to liters, which we can convert to moles using the molar mass. Not the molar mass, the molarity, right? Because this is how many moles per liter. How do we convert moles of this into grams? Yeah, we're going to use the molar mass. So remember, we're doing the sodium salt. So NaClO. So 22.99 plus 35.45 plus 16. $74.44. Grams per mole. Oops, I don't know what I'm doing. So 500 milliliters, and it's actually 500.0. We're going to convert that to liters, convert to moles, convert to grams. Milliliters down here, liters down there, moles down here. You put all the units in, and then the units tell you where to put your numbers. What's the relationship between milliliters and liters? 1,000 milliliters is equal to a liter. The other way you can write that is milli means 10 to the minus 3. So a milliliter is 10 to the minus 3 liters. Moles per liter, that's the concentration. That's this guy right here. 0.06456. It's probably two sig figs. And then grams per mole is this guy. We don't need to think about, am I supposed to multiply by the molarity or divide by the molarity? Am I supposed to divide by the molar mass or multiply? Because the units just tell us where to put the numbers.